So, I'm Lance Vincent Pascual and I will be discussing the first part of modulation. So, carrier wave. Carrier wave is a waveform, usually sinusoidal, that is modulated or modified with an input signal. So, a carrier wave is just a pure wave of constant frequency. So, ang kailangan natin malaman na ang carrier wave is just a pure wave of constant frequency. So, a carrier wave usually has a much higher frequency than the input signal. So, here's an example of a carrier wave and an input signal. So, makikita natin dito na mas mataas yung frequency ng carrier wave kesa sa input frequency. So, this is the equation in finding the instantaneous carrier amplitude. So, kaya natin makuha yung value ng carrier amplitude at any given time. Basta given ang peak carrier amplitude, ang carrier radian frequency, and carrier phase. So, recall natin na yung radian frequency is equal to 2 pi f, where f is the frequency of the wave. So, modulation. According sa Merriam-Webster Dictionary, to modulate is to change or adjust something. So, recall natin sa chapter 3 na ang modulator is a component siya ng transmitter. So, modulation is the process of varying the properties of the carrier wave with an input signal. So, kapag ibig sabihin ng modulation is babaguhin natin yung properties ng carrier wave. So, pag sinabing properties, either amplitude, frequency, or phase, or combination ng tatlo, ng any dun sa tatlo. So, that means kung hindi natin minodulate, carrier wave lang siya. Wala siya ganong information. So, this is an example ng transmitter. So, this is the audio signal. So, ito yung input signal natin. So, ito yung oscillator natin which produces the carrier wave. So, makikita ulit natin dito na yung carrier frequency is mas mataas siya kaysa dun sa input frequency. So, this is an amplitude modulator, which means na ang binabago dito is yung amplitude ng carrier wave while keeping the frequency constant. So, i-modulate muna natin yung input signal bago natin siya padaanin idaan sa channel, or yung channel dito is an antenna. So, the modulator is a component of a receiver which is discussed in chapter 2. So, the modulation is the process of extracting the original information bearing a signal from the carrier wave. So, kung yung modulation is part siya ng transmitter, i-modulate muna natin yung signal, yung carrier wave, bago natin siya padala sa channel. Yung demodulator naman is nakadaan na siya sa channel. So, ito na yung part na siya ng receiver. Ito na yung modulated signal natin. I-extract niya ngayon yung input signal doon sa carrier signal. So, again, mas mataas yung frequency ng carrier signal kesa sa message signal. So, if yung modulator natin is binabago yung amplitude ng carrier wave while keeping the carrier frequency constant, ang tawag doon is amplitude modulation or AM. So, AM, yung mga AM radio station natin, amplitude modulation ang ginagamit. So, here is low amplitude and then high amplitude and then another low amplitude. So, if yung modulator naman natin is binabago yung frequency ng carrier wave while keeping the amplitude constant, so ang tawag doon is frequency modulation, so or FM. Yung mga radio station na FM na radio, frequency modulation yung ginagamit nila. So, reasons for modulation. So, bakit ba natin kailangan ng carrier wave at modulation? Ba't hindi na lang natin ipadala sa channel yung input signal directly? So, the first reason is interference. So, if this is one station and this is another station, if hindi nila minodulate, that means na yung tinatransmit is audio signal. So, ito rin, audio signal. So, same sila ng frequency. Then that means magkakaroon ng destructive interference. So, magdi-distort ngayon yung makukuha ng receiver. So, dalawang boses na sabay, yun yung makukuha ng receiver, which is hindi siya effective. So, the second reason is frequency assignment. So, if yung one station is ginagamit is 2 megahertz and then yung another is 6, then yung difference niya is large, which means hindi siya makaka-apekto. Hindi makaka-apekto yung isang signal dun sa isa. So, paano nangyayari yun? So, recall natin sa chapter 1, yung filter. This is a bandpass filter. So, kung saan na pili lang yung frequency na ina-accept niya. So, ito yung bandwidth niya. So, nire-reject niya yung iba. So, let's say na yung filter natin is ina-accept niya is 90.7 megahertz. So, love radio yan dito. So, that means na dito sa cutoff, sa first cut, lower cutoff, hanggang dun sa upper cutoff, yun lang yung kukunin niya. That means na kapag may pumasok na 101.1 megahertz, i-attenuate niyan or i-reject niya. Hindi niya kukunin yon. So, that means na 90.7 lang yung maririnig natin or yung marireceive ng receiver natin. So, yung third reason is the height of the antenna. So, kinompute ng engineers na sabi nila na yung height ng antenna natin dapat is 1/4 siya ng wavelength. So, this is the formula for the velocity of a wave. So, velocity is equal to frequency times wavelength. So, ang velocity natin is constant since electromagnetic wave yan. Ang velocity natin is equal siya sa speed ng light. So, recall ulit natin sa chapter 3 na yung voice frequency is a very low frequency signal. So, ito yung value niya. So, if constant yung velocity and then mababa yung frequency, that means mataas yung wavelength natin. So, kapag hindi natin minodulate, mataas yung wavelength natin, mataas yung height ng antenna. Yung height ng antenna natin naaabot siya sa kilometers, which is very impractical saka impossible. So, dito ulit pumapasok kung bakit mas mataas yung frequency ng carrier wave. So, if mataas yung frequency, constant yung velocity, that means mababa yung wavelength. And if mababa yung wavelength, bababa rin yung height ng antenna. So, the fourth reason is multiplexing. Multiplexing is a method by which multiple signals are combined into one signal. So, bakit natin kailangan ng multiplexing? Nagagamit tayo ng multiplexing para makatipid. So, if this signal is an audio signal and then nakabukod siya, separate signal, that means it has a separate channel, separate carrier wave, and another signal which is, for example, a video signal, another carrier wave. So, it will become more complex. So, more costly rin kasi dalawang carrier wave yung magagamit imbis na isa lang. So, kapag nag-multiplex tayo, multiple input signals are combined into one signal. So, this is the summary of my report. So, a carrier wave is just a pure wave of constant frequency. So, ito ulit, carrier frequency is larger than the input frequency. So, yung modulator is part ng transmitter. So, yung modulation is just varying the properties ng carrier wave, either amplitude or frequency, or yung phase. Pwede rin yung phase. So, yung demodulator naman is part siya ng receiver. And these are the 4 reasons kung bakit kailangan natin gumamit ng modulation. So, yun lang po. Thank you.
Hello everyone, I am Shams D. Andrada from group number 4 and I am here to present about modulation index and bandwidth. Modulation index is also called as coefficient of modulation, modulation factor, or modulation depth. The modulation index simply describes the amount of amplitude change of an AM signal. The modulation index is equal to Vm over Vc, where Vm is the peak voltage of an intelligent signal input or the modulating signal input, while Vc is the peak voltage of the carrier signal. If we are given an AM signal where we don't have an actual value of Vc and Vm, we can get the value of the modulating signal is equal to the maximum voltage of the AM signal minus the minimum voltage of an AM signal, while the carrier voltage is equal to the maximum voltage of an AM signal plus the minimum voltage of the AM signal. If we have the carrier voltage and the modulating voltage instead, but we don't have the maximum voltage and the minimum voltage of an AM signal, we can find the maximum voltage of the AM signal equal to the Vc plus Vm, while the minimum voltage of the AM signal is equal to Vc minus Vm. And the percent modulation is equivalent to modulation index times 100%. Classification of modulation index. There are 3 classifications of modulation index. The under modulation, where Vm is always less than Vc, allowing our modulation index be less than 1, and the AM signal always looks like this. During perfect modulation, we have Vc is equivalent to Vm, allowing our modulation index be equal to 1. And the AM signal will always be looks like this. And during under modulation, we have Vm is greater than Vc, allowing our modulation index be greater than 1. Overmodulation and distortion. The modulation index should always be between 0 and 1. So ideally, when we have an amplitude modulation, the modulation index should either be undermodulated or perfectly modulated. If the amplitude of the modulating voltage is higher than the carrier voltage, we have M greater than 1, causing distortions. So during overmodulation, there would always be distortions. If the distortion is great enough, the intelligible signal will always be unintelligible. The distortion of voice transmissions produces garbled, harsh, or unnatural sounds in the speaker. Distortion of signal produces a scrambled and inaccurate picture on a TV signal. Sidebands. Side frequencies or sidebands are generated as part of modulation process and occur in the frequency spectrum directly above and below the carrier signal. In general, a narrow bandwidth or sidebands is desirable. Okay. Bandwidth is simply the difference between the upper and lower sidebands, where this is our lower sideband and this is our sideband, while this is our carrier frequency. During the carrier frequency, this is the time when our voltage is always maximum. And the bandwidth, as said before, is equivalent to the frequency at the upper sideband minus the frequency at the lower sideband. And the voltages at the lower sideband and the upper sideband is always equivalent to the half of the maximum voltage or the voltage during the carrier frequency. We have sample problems. A standard AM broadcast station is allowed to transmit modulating frequencies up to 5 kHz. If the AM station is transmitting on a 980 kHz, what is the sideband frequencies and the total bandwidth? In this equation, we are given a modulating frequency of 5 kHz and we are given a carrier frequency of 980 kHz. So the solutions would be the lower sideband would be the upper sideband would simply be the carrier frequency plus the modulating frequency be equal to 985 kHz, but the lower sideband would be the carrier frequency minus the modulating frequency, and it is equal to 975 kHz. While the bandwidth is equivalent to the upper sideband minus the lower sideband, and it would be equal to 10 kHz. Or we can also solve for the bandwidth be equal to 2 times the modulating frequency, and that would be 2 times 5, and it also be equal to 10 kHz. Another question, we have a given the input of an AM modulator is 500 kHz carrier signal with an amplitude of 20 volts. The second input is up to the AM modulator is the 10 kHz modulating signal with plus and minus 7.5 volts peak. Determine the following: the lower sideband and the upper sideband, modulation index and percent modulation, peak amplitude of the modulated carrier, and upper and lower side frequency voltage. And lastly, the maximum and minimum amplitude of the envelope or Vmax and Vin. Okay, for the upper sideband and the lower sideband, it's similar to how we solved earlier. We have given the carrier frequency of 500 kHz and plus minus the 10 kHz modulating frequency. And this is it. 5 kHz, 510 kHz, and 490 kHz. The next question, modulation index and percent modulation. So the formula for the modulation index is Vm over Vc, while the percent modulation is the modulation index times 100%. So we have this. Lastly, we have the peak voltage, peak amplitude of the modulating carrier. It is given right away. It is 20 volts. While the upper and lower sideband frequency voltage, it is equivalent to the modulating index times the peak voltage of the carrier over 2. Or it is also equal to the peak voltage of the modulating signal over 2. And lastly, we have the maximum and minimum voltage of the envelope. It is simply equal to the modulating signal voltage plus the carrier voltage is equivalent to 27.5 volts, while the V minimum is simply equivalent to the voltage of the carrier minus the modulating signal, equivalent to 12.5 volts. And this is where my presentation ends. Thank you.
Psst. Good afternoon, guys. My name is Jasper John de Cruz, and I'm about to talk about amplitude modulation. But wait, first of all, what is amplitude modulation? Well, as we can see from the name itself, amplitude modulation, to alter the signal. Sounds basic, right? But the best way that we can describe it is the superimposition of a characteristic of an intelligent signal, also known as a modulating signal, to a carrier signal. A modulating signal is often known as a information. It is also known as the data, and it's often the thing that we need to know in a signal. But yeah, an example of this signal in communication is what we produce, known as voice. Voice is created by our larynx, our mouth, and our tongue, where they cooperate to generate this signal known as speech. And yeah, so on and so forth, voice. But yeah, moving forward, in the realm of signals, our voice doesn't really cut it when it comes to travel. It tends to cut off and disappear in the vast plane. This is where carrier signal enters. Carrier signals are very high in frequency. They are often around 100 kHz and above. Well, 100 kHz isn't really high since it's still considered within the range of the low frequency signal, but you get a picture. The modulating signal travels along the carrier signals, going out on a modulator, getting demodulated by a demodulator, and so on. The discussion of this would be further discussed by the following groups, and the modulated index is to be discussed by my groupmate Shamwell on the next part. But well, yeah, moving forward, the fun thing about discussing a topic is its origin. The first recorded instance of the use is in 1901 when it is transmitted by a Canadian engineer named Reginald Fessenden. To achieve this, he used a continuous spark transmission and placed a carbon microphone in the resistance. In turn, this varied the intensity of the transmission. Although very crude, signals were audible over a distance of a few hundred meters. The quality of the audio was not really particularly good since, it's a prototype and a lot of noises were in present. Thus, it's really not that good. But yeah, because of this, it is known to be the dawn of AM. Well, yeah, moving forward, history really teaches us one good thing about, a lasting invention. And that is the advantages and disadvantages of AM. Moving to the advantages. Advantages of an AM. It is simple to implement. It can be demodulated using a circuit consisting of really few components. AM receivers are very cheap and has no specialized component needed. But yeah, moving to the disadvantages, I would rather call someone, namely Andrew Dalumpines, to read the following. Jasper, make sure to make him stand. If not, you could call another person or you can do it by yourself. But yeah, fun. An AM signal is composed of three parts. The carrier, the two side bands, the upper and the lower one, and it is enclosed by what we call an envelope. But more of that in the future discussion since AM has a lot of forms. It could be a double-sided full carrier, it could be a double-sided suppressed carrier, it could be a single-banded full carrier, and so on and so forth. But yeah, what is electronics without some math? We can actually derive the value of AM from its input, the modulating and the carrier signal. I mean, okay, just look at the derivation from the slides and we can see that it's simple. Addition, multiplication, and a bit of trigonometry. All these things aside, the derivation doesn't refer to all forms of AM. This is the basics of the value of an AM signal. But yeah, we come to a general equation for that as shown in the slide here. So yeah, this is the end of my part. Hope that you boys and girls learned something. Now I pass my mic to Shams. Again, my name is Jasper John De Cruz, also known as Jaspy. And yeah, that's all. Thank you. Bye.
Good afternoon. I'll be discussing about the power calculations in the amplitude modulation. So first, the unmodulated carrier power. The formula is P sub C is equal to V sub C RMS squared over R is equal to E sub C squared over 2R, where P sub C is the unmodulated carrier power, which is expressed in watts. R is the load resistance, expressed in ohms, E sub C is the peak voltage of the unmodulated carrier in volts, and V sub C RMS is the RMS voltage of the carrier, also in volts. Lower and upper sideband power. Because we know lower sideband is equal to the upper sideband, PLSB is equal to PUSB. N is equal to VLSB RMS squared over R is equal to P sub C M squared over 4, where PLSB is the lower sideband power, PUSB is the upper sideband power, VLSB RMS is the lower sideband RMS voltage. In volts, P sub C is the unmodulated carrier power. In watts, M is the modulation index, which is unitless, and R is the load resistance in ohms. The total transmitted power is expressed as P sub T is equal to P sub C plus P sub LSB plus P sub USB, which is also P sub T is equal to P sub C times the quantity of 1 plus M squared over 2, where P sub T is the total transmitted power. In watts, P sub C is the unmodulated carrier power. In watts, P LSB is the lower sideband power, also in watts, and PUSB is the upper sideband power. M is still the modulation index. So this is the power spectrum for the amplitude modulation DSBF C wave with a single frequency modulating signal. Percent power in the carrier. Percent P sub C is equal to P sub C over P sub T is equal to P sub C over P sub C 1 plus M squared over 2, where percent P sub C is equal to the percent power in the carrier, which is expressed in percent. P sub C is the unmodulated carrier power. In watts, P sub T is the total transmitted power, and M is the modulation index. Percent power in the sidebands. Percent PSB is equal to PSB over PT is equal to P sub C M squared over 2 all over P sub C times the quantity of 1 plus M squared over 2, where percent PSB is the percent power in the sidebands, P sub SB is the power in the sidebands, P sub T is the total transmitted power, P sub C is the unmodulated carrier power, and M is the modulation index. Additional info. Among the three signals comprising AM, only the sidebands contain the information. The information found in the upper sideband is identical with the lower one. At 100% modulation, 66.67% of the total power is contained in the carrier, and only 33.33% is in the sidebands. It is wasteful to submit the carrier, and is redundant to transmit both sidebands. So we go to the voltage calculations. E sub T is equal to P sub C multiplied by the square root of 1 plus M squared over 2, where E sub T is the peak voltage of the modulated carrier. In volts, E sub C is the peak voltage of the unmodulated carrier, and M is the modulation index. The current calculations formula is I sub T is equal to I sub C times the square root of 1 plus m squared over 2, where I sub t is the peak current of the modulated carrier. I sub c is the peak current of the modulated carrier in amperes, and m is the modulation index. So, a few examples to make use of the formulas. So the first example is determine the maximum upper, lower, and total sideband power for an unmodulated carrier power of 2000 watts. So the given, which is 2000 watts or 2 kilowatts, is P sub C. So to get the total sideband power, you must get this formula. PUSB is equal to PLSB is equal to P sub C m squared over 4. And substitute correspondingly. P sub C is 2 kilowatts. M is 1. And we get, and the corresponding upper sideband and lower sideband power is 500 watts. Number 2. Find the total transmitted power for the AN system in the previous example. So we are still given the same set of values, but with a different question. Now we shall get the total transmitted power. So the formula is P sub T is equal to P sub C times 1 plus m squared over 2. P sub C is still 2 kilowatts and m is still 1. So the answer is 3 kilowatts. Number 3. Find the percent power in the carrier in the previous example. Still, P sub C is 2 kilowatts. So, get the formula. Percent P sub C is equal to P sub C over P sub T. P sub C is the modulated carrier power, 2 kilowatts, and P sub T is the total transmitted power, which is 3 kilowatts. So, divided, and we shall get 66.67%. Number 4. Find the percent power in the sidebands in the previous examples. So, in this question, we shall get the sideband power. Percent power in sidebands. So percent PSB is equal to PSB over PT, which is equal to P sub C m squared over 2 all over P sub C 1 plus m squared over 2. So substitute accordingly. P sub C is still 2 kilowatts. Modulation index is 1. And we get the final answer, 33.33%. Number 5. An antenna has an impedance of 40 ohms. An unmodulated AM signal produces a current of 4.8 amperes. The modulation is 90%. Calculate the carrier power. So this is a different set of values compared to the previous examples. So to get the answer in this one, the formula P sub C is equal to I squared R will be used, wherein P sub C is the carrier power, I squared is the current, and R is the resistance. So substitute accordingly. 4.8 amperes times 40 ohms, and get the carrier power, which is 921.6 watts. Number 6. From the previous problem, calculate the total power and the sideband power. So from number 5, we are asked to calculate the total power and the sideband power. For this question, we need these formulas. I sub t is equal to I sub c multiplied by the square root of 1 plus m squared over 2. Substitute accordingly. I sub c is 4.8 amperes, m is 0.9, and the total current is 5.7 amperes. And from there, E sub t is equal to I sub t squared R. The total current is 5.7 amperes. The R is 40 ohms, and the total power is 1295 watts. Finally, PSB is equal to P sub T minus P sub C, which is the sideband power, which is equal to 1295 watts minus 921.6 watts, which is equal to 373.4 watts, which is final answer. Note that because there are two sidebands, each of them gets 186.7 watts. So that's all. Thank you.
Hello. Hello. Today we'll be going over amplitude frequency. Specifically, we'll be going over the topic of simultaneous modulation. So in this topic of simultaneous modulation, we'll be focusing on only one type of AM transmission. So as you can see, there are a lot of types of AM transmission, but we'll be focusing on the A3E standard AM DSBFC double sideband full carrier, which is used for broadcasting. So the frequency domain of the DSBFC standard AM looks like this with 3 arrows. The 3 arrows are represented by the carrier frequency, the upper sideband frequency, and the lower sideband frequency. So the carrier frequency, which is FC, the upper sideband frequency is the carrier frequency plus the modulation frequency. The lower sideband is the carrier frequency minus the modulation frequency. So as we've discussed, this is an A3E standard AM DSBFC. So we have the carrier frequency in the middle and the sideband frequencies. The left is the lower sideband frequencies and the right is the upper sideband frequencies. So following this, if FM3 is greater than FM2 is greater than FM1, then our bandwidth would be equal to the upper sideband frequency minus the lower sideband frequency, and this becomes the carrier frequency plus the highest modulation frequency, which is the upper sideband, minus the carrier frequency minus the highest modulation frequency, which is the lower sideband. So this becomes 2 FMH. So this bandwidth BW is equals to 2 FMH, and this represents our simultaneous modulation. So FMH stands for the highest modulation frequency in Hertz units. So the formula for the modulation index for simultaneous modulation is represented by m sub t equals the square root of m sub 1 squared plus m sub 2 squared plus m sub 3 squared plus and so on up till m sub n squared, where m sub t represents the total or effective modulation index, m sub 1 represents the modulation index of the first tone, m sub 2 represents the modulation index of the second tone, m sub n represents the modulation index of the nth tone. So we'll be going over two examples. So for our first example, it starts with how many AM broadcast stations can be accommodated in a 100 kHz bandwidth if the highest modulating frequency is 5 kHz. So we are given 100 kHz of bandwidth and 5 kHz, which is the highest modulating frequency. So it is FMH equals 5 kHz. So to solve for this, we'll be solving for the simultaneous modulation for the bandwidth, which is 2 times FMH. So 2 times FMH is equals to 5 kHz, so 2 times 5 kHz. So this becomes 10 kHz. So this is the simultaneous modulation bandwidth. So 10 kHz goes into 100 kHz 10 times. So how many AM broadcast stations can be accommodated? That will be 10 stations. For our last example, an AM transmitter is modulated by two audio tones at 1 kHz and 2.5 kHz with modulation depths of 0.25 and 0.50 respectively. Find the effective modulation index. So to visualize this, we have the diagram, carrier frequency, sideband frequencies, and our first audio tone will be 1 kHz, which will be, say here, which is FC. Then yeah, and this is where 2.5 kHz lies. Okay, so for our first modulation index would be 0.25, and the second modulation index would be 0.5. To solve for this, we'll be using m sub t. M sub t is equals to the square root of m sub 1 squared plus m sub 2 squared. So m sub t is equals to square root of 0.25 squared plus 0.5 squared. So m sub t is equals to 0.56. So our effective modulation index is 0.56. Thank you.